Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending today's presentation, Don't Blame the Adhesive, It Never Had a Chance. Today's presentation is being recorded, and you will be able to access both the recording and presentation slides once they are available online, usually within 24 hours. If you have any questions during the webinar, please use the GoToWebinar question tool. You may submit a question at any time during the presentation, and we will reserve time at the end of the webinar to answer as many questions as we can. Today, our expert panel will dive into the reasons adhesives fail and provide you with insights to help your operation succeed with your adhesive applications. Topics include a review of the principles and fundamentals of good adhesion, common chemistries used when matching adhesives to specific applications, what adhesive failures reveal, how to prepare surfaces for better adhesion, customizing materials for adhesive success, and again, we'll leave time at the end of the presentation for your questions. Next, I'd like to introduce our panel for today's webinar. All three of our presenters are experts in their field and have decades of experience in helping customers achieve good adhesion in their operations. Wilson Lee is Enercon's Business Development Director. He has extensive experience in surface treating applications over a wide variety of industries. Wilson works with Enercon customers on developing flame and plasma technology solutions to solve their surface treating challenges. Wilson earned an electrical engineering degree and an MBA from Clemson University. Bonnie Ludwig is Director of Product Development at Resin Lab, a division of Ellsworth Adhesives. Bonnie has over a decade of experience leading the formulation and technology development of custom silicone, epoxy, and urethane adhesives. She received her PhD in materials chemistry from the University of Michigan. Don Giroux brings over 45 years of experience in the specialty adhesive industry to our presentation today. In addition to working for several of the leading adhesive manufacturers, as an entrepreneur, Don has also started multiple adhesive companies. Don currently works with Resin Lab as a technical consultant and in research and development. For those of you not familiar with Enercon or Resin Lab, we'll briefly touch upon some of the highlights. Enercon was established in 1974 in Wisconsin. Today, Enercon is recognized as the global leader in corona, plasma, and flame surface treating technology. Enercon serves manufacturers around the world with an international network of operating centers and representatives. Now I'll hand the presentation over to Don, who will tell us a little bit about Resin Lab, and then Bonnie will get the presentation started with the principles and fundamentals of adhesion.
Well, good morning. My name is Don Giroux. I work in product development for Resin Lab. I work in Dr. Bonnie Ludwig's group. And I'm going to tell you a little bit about Resin Lab. Resin Lab is part of the Ellsworth family of companies, and we have this specific responsibility towards the adhesive distribution group to provide technical support. In the late 1980s, Ellsworth was a growing concern who had a very capable group of science or technical related people in their sales force, but they had a deficiency. They had very little experience relative to the chemistries of the products they were selling. So they went out and they found a talented young chemist by the name of Paul Tien. They brought him into their group. They gave him 1,000 square feet of space, 2 mixers and a technician, and I would argue that was the birth of Resin Lab. Now fast forward to today, we have over 106,000 square feet. We have 50 plus employees. Dr. Bonnie Ludwig's group consists of a group of highly trained chemists, scientists, and technicians, and we have a state-of-the-art laboratory. But despite all this growth, we remain the same company that Paul Tien helped us start in the beginning, where we are responsible mostly for the technical support of the Ellsworth sales group and their customers.
Ellsworth, as an organization, has a commitment to quality. We have systems in place to hold us accountable to that commitment, and systems in place to organize our documents and our work. We also have a culture of continuous improvement. and we take that very seriously. And then Resin Lab services are focused mainly on custom formulations. So a customer would come in, they would have a specific need, and we would create a formula that works exactly how it needs to in their application. We also do modifications of our own and other companies' products, something as simple as a change in color or adding of spacer beads to things that are more complex. We do tool blending, which is where a customer comes in with their own formula and uses our facilities to manufacture that product. And inside of our building, we have custom packaging as well. Moving on to the principles of adhesion. So adhesives are used across many markets. This isn't even a full list, but it's a good example of all of the places that in industrial applications that adhesives are used. So as you think about adhesives, we want to think about what is adhesion and what is an adhesive. And it's very simple. Adhesion, a very simple definition would be the ability to get something to stick to something else, to have some sort of bond that would require a force to pull those two things apart. An adhesive is a material that you use between two parts that allows you to achieve that adhesion. And we're going to be talking about adhesives today. A very simple rule of thumb as far as troubleshooting is to look at the mode of failure of the adhesive. So there are two main modes of failure that are typically observed. The first is cohesive failure. In this case, the glue or the adhesive breaks apart internally. You would observe the glue still stuck to the substrate, but the glue itself has broken apart internally. The second is adhesive failure. In this case, the adhesive remains intact. It keeps its integrity, but it actually peels off of the substrate. As you go through the process of selecting an adhesive, you want to think holistically about your application, how you want your process to work, how you're going to take that adhesive and convert it from a liquid format to a solid format, and what you want those properties to be after it's hardened and it's in your application as an adhesive. Sometimes when we work with customers, they're really focused on the post-cure piece, which is the performance in the application. Really, the process piece, the process pieces are just as important as the performance in the application, and include concerns in terms of how fast your process is going to work, health and safety, and convenience for your operators. We're going to talk a little bit about common chemistries of adhesives, and this is going to be rather brief. So we've got one slide that kind of shows a whole bunch of stuff. And what I want you to take away from this slide is that there's really three main components. The first is to look at your substrates, and that's your symbol key over on the left. Directly below that, we have characteristics. So how does the adhesive behave before cure, during cure, and then after cure? And then over on the right, we have some typical adhesive types. Resin Lab focuses on epoxy, polyurethane, silicone, and UV, and UV isn't even listed on this infographic. But you can see that the mix of symbols on each type of adhesive is different. And so you would really want to take a look at your application and your process and how the product's going to be used, what type of environment it might be in, and consider that as you're making a choice of adhesive. And work with folks that can help you to make good choices that adhesive and its performance. And a consideration for you, we will be providing a copy of an infographic called Which Glue to Choose after the presentation. So moving on to what adhesive failures reveal. So your first step is to examine the mode of failure. And you may remember from a previous slide, we have two main modes of failure: adhesive failure and cohesive failure. The adhesive failure, the adhesive will separate cleanly from the substrate. So the adhesive itself is intact, but it is no longer stuck to the thing that you tried to glue it to. In that case, the bond between the substrate and the adhesive needs to be improved. For cohesive failure, the adhesive itself breaks apart, but it does remain bonded to the substrate. In that case, the adhesive type may need to be changed. So it may need to be chosen to be stronger or tougher or more elastic, depending on how much strength you need in that bond. So again, if your failure mode is cohesive, that means that your adhesive doesn't have the needed mechanical properties for your assembly to do what it needs to do. So you may need to modify the hardness, the flexibility, elasticity, strength, toughness, and probably more things as far as how the adhesive performs. You may have had an issue with applying the material. So you may have not mixed the adhesive properly if it's a two-part system, or you may not have applied enough energy or time to allow it to harden completely to its full properties. Another common reason you would have cohesive failure is that the adhesive itself is fine, but the environment of use creates changes to the material. So things like wide swings in temperature, pressure, humidity, moisture, so actually contact with water, other chemicals. So for instance, if you're in an automotive application and the material is subject to things like greases and fuel or exposure to UV, all of those things, depending on the type of adhesive you choose, may compromise the performance of that adhesive. So up front, you would want to know what the environment of use is and select the adhesive based on how robust it needs to be in that environment. For adhesive failure mode, where the adhesive just isn't sticking to your substrate, there may be a mismatch of the adhesive and the materials being bonded. So we see that with a coefficient of thermal expansion mismatch. In this, what would happen, what we typically see is that the parts are bonded and the product, the assembly, is thermally cycled. And during that thermal cycling, we'll actually see parts just spontaneously pop off of the assembly. That's due to as the assembly is heating and cooling, the different parts expand and contract at different rates, and that mismatch of CTE causes parts to just pop right off. More common with adhesive failure mode is issues with surface preparation. Surface preparation includes surface roughness, wettability, and the presence of contaminants. And we're going to spend some more time focusing on surface preparation and considerations with how to look at the surface to prevent adhesive failure as we move through this presentation. If you want to try to predict how your adhesive will perform, you can do some adhesion testing. Typical adhesive tests are lap shear testing, and that's what's pictured to the right. That is a lap shear test where two parts are bonded together with a 1/2 inch overlap and then pulled apart by a universal tester, and you can get a force in pounds per square inch. You can choose the substrate base to match it to your assembly and predict both the strength of the bond and the typical mode of failure. Other tests exist, and even more beyond what's on this list. Adhesion testing isn't a cure-all. It will be predictive of performance, but ultimately what your assembly is made of, how it is put together, and how you use it need to be examined in order to ensure that your adhesive choice and your adhesive process are the best choice to get the performance that you need.
All right, thanks, Bonnie. So now we will turn it over to Wilson, who will cover how to prepare surfaces for better adhesion.
Thank you, Mark. All right, so I get calls every day, and we work directly with Ellsworth and Resin Labs to solve a lot of problems because people will call in when they're having an issue. So many times we have to look at the surface to try to figure out what might be wrong and what needs to be done in order to improve adhesion. So in the picture there, you can see the picture of the treated side versus the untreated side. Sorry about that, Mark. The untreated side would be very similar to waxing your car. The water beads up and rolls off, or rain-exing your windshield. That is decreasing the surface energy, whereas the treated side is increasing the surface energy, so you're getting wettability. So where that wouldn't be good on your windshield, that is obviously a much better state for you to be if you're going to bond. So, all right, we can go now. Sorry about that, Mark. So what causes some adhesion impediments? Low surface energy or tension. There might be migrations or formulations in the material itself. So the plastic may have a flame retardant or something in there to make it safer, but that's going to damage or limit your ability to bond to it. There may be release agents on the surface, but other things like light and temperature, mechanical stresses, all of these things can be impediments to adhesion and cause you to have a surface that's not easy to bond to. So what we're looking at here is just a graphical representation of a low surface energy, a hydrophobic surface. Water phobic means fear, so it's repelling the water on the surface, or in this case, it may be an adhesive. Again, you might have a low surface energy, plastics in general, or low surface energy materials. That means they have limited bonding sites. There might be the contamination, and then there's the additives that you see there that might be migrating to the surface and causing a problem with that surface and making it harder to bond to. So after our treatment, we go to the next slide, and hopefully we have a much higher surface energy. We'll go over that in a few minutes. We've removed contamination that increased the bond sites, and we've taken the additives away from the surface. And we've gone from a hydrophobic surface to a hydrophilic surface, and that is a much more a better prepared surface with which to bond to. So there are a lot of options to prep the surface, and this is, again, mostly what I do every day. Someone's calling in, they're already doing something. They may be using primers, they may be etching the surface somehow with a chemical, mechanical preparation, sanding or ablation or something. They may be using vacuum plasma, they may be using other types of plasma or flame. And what we're trying to do in each of these situations is try to figure out the best way to prep the surface. As in the industry slide that Bonnie showed, almost everybody uses adhesives. Well, almost everybody uses some sort of surface preparation because they've determined that it is important to have a good repeatable surface if you're going to get good final products. And many times, the first three of these, the mechanical preparations, the etching, and the primers, they all are by hand in some form or fashion. And so that's less repeatable. So your standard deviation and your final product goes up. You have some poor product designs, you have some failures in the field, and if you move to a plasma or a flame type pre-treatment, you can predict more accurately what's going to happen after you do the bond. So here is our plasma. Plasma is just the fourth state of matter, solid, liquid, gas, plasma, and plasma is just the ionized form of the gas. So we typically use compressed air, so you're going to have ions of nitrogen, hydrogen, oxygen, and then combinations of OH and things like that that are attacking your surface. And it comes in three different forms. The one on the left, the blown ion, is what most people think of when they think of plasma. It does look like a candle flame, but that's just the UV light that's coming out. We use that to get down into crevices like that. We use it for bonding lines. You use it to treat a lot of different things. It can work on any material, pretty much any material. The blown arc in the middle has to be used on non-conductive materials. Now that's about a 3.5-inch wide head, so it is treating a larger area, but you're generally going a little bit slower, in the order of maybe 10 to 15 feet per minute, whereas the blown ion can go much faster, maybe 100 feet a minute. And then we have flame. Flame gives you the ability to go much wider, more economically. It also gives you a little bit more area with which you can treat. By that I mean, we like to say multi-dimensional surfaces is usually better for a flame treater, just because I don't have to be as accurate with my distance to the surface as I do with plasma. Plasma is very much dependent on the speed at which you're treating and the distance from the surface, and that's the ion density that you're going to get is related to both of those. Flame gives you a much larger area with which to do that, and you can, again, with a multidimensional surface like maybe a Coke bottle or something, you're trying to treat the side of that, you can see that you're going to be different distances away. So we go to flame when we do this. So what does plasma actually do to the surface? 3 things. It cleans the surface. Now, the one that's not mentioned here is once you treat something, it takes the static off the surface. So anything like dust or anything being held on by static will go away. It kind of gets blown off just by the pressure of the air. But it also can remove organic and a few inorganic materials. You see there on the left, material comes in dirty and it goes through the plasma, and the plasma will clean those organics off. Now, some of the inorganics are a little bit harder to clean, so it may take a pre-treatment step for those. But again, it does a good job cleaning those surfaces. The second thing it does is etch the surface. Now this is a micro etch. You can see that we're on the scale of 5 to 30 nanometers. But again, you've got your manufactured surface coming in on the left, going through the plasma stream, and you are etching that surface. Now you can't see this with the naked eye, but we are increasing the bondable area by about 30%. And one of the things that you need to do in order to get a better bond is to increase the area which your surface area for the adhesives to stick. And so this is the second thing that plasma does to increase the bond strength. Lastly, we're going to talk about, on the next slide, we're going to talk about functionalization. And this is increasing the polar groups on the surface. Now this is a little bit more complicated. We're actually changing the outermost molecular layers and adding polar functional groups like O2 groups, OH groups. And what that does is increases the surface energy. I mentioned before that if you rain-x your windshield or you wax your car, what you're really doing is decreasing the surface energy, so that the water in that case will just roll off and it'll be easier to see, or your car will stay clean. What we're doing trying to bond is increase that surface energy. Surface energy is basically related to the strength of the atoms that are holding the molecules, or the strength of the bond holding the molecules together. So if I have a block of polypropylene and I try to cut through that, all you're really doing is cutting the bonds. And that's pretty easy to do because plastics have low surface energies. If I've got a block of titanium, I'm trying to cut it, the bonds between the titanium atoms are much stronger, and so the surface energy is higher. So we have to look at that starting surface energy to see where we're going to be and what ability you're going to have to bond to it. And then once you plasma or flame treat it, we're hoping to increase that by increasing those polar groups on the surface. And then once the bond is made, then that is a permanent bond. So how do we test it? We use dyne solutions and contact angle. Now, when I do dyne, the higher the dyne level, the higher the surface energy. And in general, this is not 100%, but in general, the higher the surface energy, the better your ability to bond to a surface. So again, we use dyne. The range is from around 30 to about 72. The higher you go on the dyne level, the higher your surface energy. You can see what you would do in this case if you were using a dyne pen and you were trying to test, say, at 50, and you would mark a line like you see over there on the right side. If that line collapses on itself really quickly, it is said to have failed that, so the dyne must be lower. But if it marks it like the Sharpie type mark underneath the correct dyne level, that means it passed at 59 and your surface is at least at 59. So if you're using this in manufacturing, you may have decided in engineering trials okay, I need at least 50 dyne to get a good bond, and so you would do that test. Contact angle is a little more accurate. We use it in our lab every day to get better information. In this case, you're actually using two different materials, a polar and then a dispersed energy unit to measure the surface energy. And once you've treated, hopefully the first slide there is pre-treatment. So contact angle, you'll see the water is beating up on the surface. And then the second image there, after you've treated, you can see that it flattened out. And so the water is spreading out, similar to that picture of the treated slide up top. So that's how we measure those. They're not perfect measurements. They are not absolute measurements. And by that, I mean, if I measure my phone, it's 5 or 6 inches across, and I mail it to you wherever you're at, it's still gonna be 5 or 6 inches across. Contact angle and dyne solutions are not that way. There's a lot of atmospheric things that are gonna affect that and the way the treatment method is going. So you can get slightly different numbers, but what we're really looking for is a delta, a large change in either the dyne or the contact angle that shows that we're increasing the surface energy. This is just a few materials and where they typically start on the dyne level. On the far left, you've got polypropylene, which is around 29, 30 dyne, all the way up to a polyimide that might be at 50 dyne, and then everything else across. But again, this is just to give you an idea of where these materials typically start in their surface energies. And generally, you're going to need a higher number than these in order to get an effective bond. But the only way to really figure that out is to do the testing. I'm not going to go through this slide. I want this to be in the presentation so you can look at it. But what this is showing is how you treat things differently with flame and blown ion and the different results that you get. So the first line is polypropylene. It started out untreated about 30 dyne. Once you treated it with the blown ion, it went up to 58 dyne. But the flame treater in this case did better. It went to 70 dyne. So this is one of the things that we take into account when we try to recommend a solution for you if you're having an issue. Sometimes the material just reacts better to one form of treatment versus another. Sometimes we have to look at the form of the material because, again, if I'm only treating a few square inches and I have 20 minutes to do it, well, I've got lots of solutions there. But if I'm trying to treat a few square meters or a few square feet and I've only got a couple of seconds, well, that's going to limit the number of applications that I can do. So we look at this to try to figure out what is the best way to treat it. But many times it's the actual form of the material that we're treating that decides what we're going to try to do. And this was a lab test that we did with a polyethylene with a UV cured adhesive. And after 24 hours, you can see that the bond strength more than tripled from our control using both the blown ion, which is the plasma, and the flame plasma. And this was happened to be a Hinkle adhesive that we use in the control test. This is just kind of showing you the difference in bond strength that you'll get after treatment. So now let's look at the effectiveness. How do we figure out the effectiveness of the treatment? So here, this is, again, I think Bonnie mentioned this as well. Just doing the test in our lab or in resin lab is not going to be sufficient. We really need to do the test at your facility and run these with your materials and everything. That's we use dyne and contact angle to show the difference in surface energy after our treatment, but it's really just an indication of where we're at. We really need to run the trials and run the tests at your facility. We get asked a lot, mostly by aerospace, how do I know that I've got a good bond without breaking it? And the way we do that is try to control as many things in the process as we can before it comes into our system and then out of our system. So by that I mean, I can predict with pretty good, well, with a very low standard deviation of error, how something is going to come out of my flame or my plasma system if I know the material that goes in. So we have to monitor each of those steps and know where we're at, know how clean the material is, know what the surface energy of the material is, and all of those things, and then know what level of surface energy we need for a good bond to come out on the other side and have a good part. So that's how we try to control each of those steps. But again, it is very important to do this in your facility with your materials, with your production, and then we can determine or help you determine what level you need and what level of treatment you need. The other question gets asked all the time is how long does the treatment last? And this could be, again, from hours or actually seconds in the case of fluoropolymers which don't treat very well, to several months. We do have some batch applications, not very many, where somebody treats a part and then they put it in a batch and then they print on it or something later. That can happen if you only need a slight increase in surface energy, but it's not optimal. You're creating a highly active part, so we always recommend that you do whatever the next process step is, in this case bonding it, as soon as possible after the treatment. It leaves the least room for mistakes and things to happen. So you want to do that as quickly as possible, but technically you can have 2 to 3 to 4 days before the treatment goes down, but we do measure that, and we can send you samples at different levels, and then you can test those levels and say, okay, we need above 59 or 69 or 49 or whatever it is in order to make the part that we're looking to make, and then we can work with you on how to do that repeatedly. So let's look at a couple of applications. This was a case study that we did with Resin Lab. We were using high density polyethylene in a clear Resin Lab adhesive. We put these together and then we did a pull test on it. We did some treatment. We did clean it first, and then we tried the plasma treatment and then the blown arc treatment to see, the flame plasma and the blown arc treatment to see what gave us the best results. And then the one sample that was not treated was just cleaned first, and then we did the flame and the blown arc without treating it. Initial 9 level for both was 33, and then you can see that even we got the same 69 after treatment. That's a nice delta there. That's a good repeatable number that you can use. And then we did the pull testing on that, a 1 inch by 4 inch lap shear coupons, and then they were pulled apart within 45 minutes of treatment. And you can see the white treatment had 120 psi of strength, and then in this case, it looks like the flame plasma did better on the pull test at 443, and the blown arc still did much better than the 120 at 393. So again, this is a case study that we did showing the difference of just what can happen if you treat that material. You're increasing the energy on the surface, and you're going to get a better bond. Some other applications that we've gotten into in the past, the headlamp is probably the original plasma application. Many older cars, you could see those headlamps fill up with water because they weren't sealed very well until they started using plasma to treat the polycarbonate lens and the housing, which is polypropylene, and you treat inside that gap. You put the adhesive in there, and once you seal it, now you've got a good solid seal. And you very rarely see the headlamps filled up with water these days because of a poor seal. So this is just an example of what plasma can do to increase that bond strength. Another interior panels for cars, dashboards, side panels. They're almost always done with flame. And the reason again is the multi-dimensional surface. You can see the dashboard on the far right there and the flame trying to treat that. There's a lot of convex and concave areas on that, so treating that with the flame is very fast. You can do it in just a few seconds, and you get a good consistent treatment on there before they put the decorative coating on there. And then of course you see the door panel a little bit left of that. This is the flame solution, but then they would put the adhesive on and then whatever decorative coating that you're going to have in that type of vehicle. That's usually a polypropylene, or sometimes it's a fiberglass dash or door panel. We do a lot of potting applications too for outdoor electronic circuits. Going back to the headlamp assembly, each one of those headlamp assemblies also has an electrical circuit to it that is potted in a very similar way that you see right there. It can be treated with plasma or flame. Flame is usually faster, and we'll get down into the cracks and crevices a little bit better than plasma, but plasma is also used in this application. And what we're doing is trying to increase the surface energy of all those different little components that are on that circuit board and the shell itself, so that the epoxy sticks to that and you don't have a failure route where water can get into the circuit and destroy that. Another application for bonding, and there's lots of applications here, but this is a window and door application. There's about 8 different bonding applications in this part. Sometimes we're bonding the frame to the frame, sometimes we're bonding the glass to the frame, sometimes we're bonding plastic to the frame. So there's a lot of different applications here, and we have a lot of different nozzles that we use with the blown ion to try to get down into some of those highly intricate pieces there. You can see the side profile of that particular glass or window. There's always a very unique profile depending on the manufacturer, and so sometimes you have to create different manufacturing tools to get down in there. But again, this is another good bonding application. You're usually using a PVC or some other plastic for the window, which is again low surface energy, so treatment is necessary to get the good bond. And customizing materials for successful adhesion.
All right. So thank you, Wilson, for that update on the surface treating applications. We're going to pass it over to Don now, who's going to talk about some of the things that Resin Lab works on in customizing materials.
All right, thank you. As I stated earlier, it's important to understand that Resin Lab's primary responsibility is to the technical support of the Ellsworth Adhesives distribution network. So we at product development are not really getting applications associated with materials that would satisfy a broad industrial sector. Ellsworth Adhesives has partners and principals that do a very, very good job of doing that sort of thing. So the kind of projects that we get are more associated with a custom opportunity. So we have a customer who is in need of a product. He can't find a commercialized product that works in this type of application. So they bring it to us, and we make a product specific for them. So that's kind of what drives our product development efforts, which also means that we end up with some unusual products. So I'd like to touch on those just quickly, just a few of them, just to give you a flavor for the kind of things that we're making. 10 unique products. I hope it's 10. In any case, UV silicone, kind of unique product. It was a gasketing type of application, I believe. It was needed to be dispensed onto a plastic substrate, and exposed locations would be hit with UV light to immobilize it so that the device could be moved down the production line. Condensation cure continues in dark sections, and within 24 hours, there's a complete cure. A little unusual product, but a very good one. It's also a pretty color. I think that's an important thing to note. Next slide, please. High temperature epoxies. This is a blast from the past in the sense that when I first got into this business, there was a lot of people that needed high temperature epoxies, mostly because people weren't particularly good at thermal management. But today, that's not a very common thing, and yet we have been asked to make a product that is very high in temperature capabilities with a TG in excess of 200 degrees C. It maintains great compression and bond strengths up to 200 degrees C, low ionics, high thermal conductivity, low coefficient of thermal expansion, and suitable for very large castings because at very low exotherm, it's a slow reaction. But it's only unique because of the fact that it's just not done that often these days. The UV gel two-part epoxy. We've actually made a UV gel two-part epoxy and a urethane. So this is typically applications where somebody is using, in this particular case, an epoxy adhesive, and they're, say, shooting it into a small sensor. And the material is getting underneath the board, and it's taking either a heat cure oven or 12 to 24 hours to polymerize. And some smart engineer decides, hey, I'd rather do this thing quicker. So we modify the product so that once it fills the device, it's hit with UV radiation. It polymerizes on the top surface. The product can then move down the line, go to secondary processes, and the secondary cure completes after a period of time. Electrically conductive adhesives. Frankly, a lot of people make electrically conductive adhesives. The reason I wanted to include this one is it's a little unusual in the sense that it can be used in side-by-side cartridges.
with very, very small static mix heads. So we can take this very expensive product, and it's a relatively good adhesive with very high electrical conductivity, and we can deliver small amounts to electronics and basically save costs. So it's only really unique in the sense that it is a room temperature cure product that is delivered in a 1-to-1 side-by-side cartridge and can be mixed efficiently through a small static mix head. Foaming silicone, I frankly don't remember what we made this for, but it is a unique product. Picture once again, a side-by-side cartridge dispense of this product into an orifice of some sort, and then it goes into a foam and cures. So it's very good for certain types of applications like foam in place gasketing. It has very low compression set and can be made fire retardant. Non-MVP UV PET adhesive. For many years, people were bonding to low surface energy plastics by modifying their acrylic-based UV cure material with N-vinyl pyrrolidone. Vinyl pyrrolidone is actually, I guess, has a solvent to the surface. It allows a little bit better bite for the UV cure to the material. So in the case of PET, for example, it usually provides a substrate to substrate failure with PET. Unfortunately, MVP is on a naughty list, and people are trying to get it out of their polymers. And we've been asked to make one without the MVP, and we managed to do that. It's also particularly useful for other low surface energy plastics as long as it's used with plasma treatment. High thermal conductivity silicones, in excess of 1 watt per meter K with low viscosity, usually would be of value in applications associated with battery packaging along those lines, but a very good thermally conductive material. And I think the next slide is the high thermal K epoxy. Similar excess of 1 watt per meter K, low viscosity. This particular product has very high adhesion to, I think it was a nickel aluminum substrate that was used. And it is also available in side-by-side cartridges. So there's some advantages with that one as well. 3D printed polymer. This is kind of interesting, and this is new to us in the sense that 3D printing, they're going to be printing everything soon. So we were brought an opportunity where the particular company doing the 3D printing was making very, very large devices, like theoretically a chassis to a car, or the enclosure for a car. And the shrinkage associated with these polymers is a real issue. Acrylic materials, which are normally used for these 3D printing applications, have an enormous amount of shrinkage. In the unfilled state, they could be as much as 10%. So we were tasked with coming up with something that would still fit into a 3D printing process, still use light radiation cure to polymerize, yet they wanted two things. They wanted much lower shrinkage and the ability to put opaque materials into the polymer and still allow a UV cure. So we have come up with a product that does this. It's kind of unique. We need to find a partner for this one, but again, I just wanted to give you a flavor for some of the interesting products that we have going. And the shrinkage in the filled state would be about 1/10 of that of a conventional UV printing acrylic resin system. Foam in place gasket, there's people that do this in the industry. The only reason I included this one is because of the fact that we use a little bit different cure chemistry in this particular one. We have a gasket that a gasket material that we made for a very specific application that required extremely low water vapor transmission because it's trying to protect some electrical components. So this particular one has extremely low water vapor transmission capability, and in addition to that, it stays flexible to -65. A pretty robust system. There are other people that do it, but I think this is a unique approach.
All right, Don, thank you for that. We have a lot of questions coming up, but before we get to those, let's take a quick recap of some of the topics presented today. Always remember to select a suitable adhesive based on the application, process, and performance specifications. Know that adhesive failure is most likely due to issues with surface preparation, and cohesive failure is most likely due to the incorrect choice of adhesive. The Resin Lab team is here to help you with the challenging projects when commercially available products do not meet your application needs. The team's experience, lab capabilities, and their ability to create custom engineered formulations offer you a great resource for those projects. And when it comes to preparing a surface for adhesion, Wilson and his team at Enercon provide you access to the industry's widest range of plasma and flame treating technologies. They also offer free lab trials in their facilities, as well as trials that can be conducted at your facility to determine the effectiveness of treatment for your application. With that, we'll switch over to the questions and answers. Note that if you do have a more complex question or want to reach out to any of our presenters, you've got some contact information below with the phone numbers and email addresses. And so let's get into your questions. The first one is, are surfactants used to adjust the wettability of adhesives? I'm not sure if Bonnie or Don, do you want to take that one?
They're asking about surfactants?
Surfactants, correct.
Probably surfactants.
Don, do you want to take that one?
Yeah, I think that is a common approach, usually more in the coating industry than the adhesive industry. Wouldn't you say that's true, Bonnie? But in the coating industry, it's done quite a bit, and the concern there, of course, is not just functionality, it's aesthetic. So there are a number of different types of additives that can go into those types of polymers that are designed to provide a nice uniform consistency to the coating. We don't really use them in adhesives.
Yeah, and I think part of the reason we don't tend to use them in adhesives is because I think in coatings, maybe the bond strengths may be lower than the structural adhesives that we're making, which are very, very strong. Those surfactants, we would need to make sure that they were not changing those cohesive properties of the product that we make and compromising something about either the material or the bond. You know, anything that you have that's like surfactants, we normally think about those as not bonding into the structure of the adhesive, and anything that's sort of loose out there, we would kind of you know, try to avoid. If you agree with that, Don?
Absolutely. It's not in the best interest to have floaters, as we call them. Everything should be reacted if possible.
Yep.
Thanks, Bonnie and Don. Wilson, this is a question regarding surface treatment. Would surface treatment allow a customer to use HSE adhesives on LSE substrates?
I wish I knew the answer to that one without testing it, but I don't. Sorry. So, but we can do that in our lab, or we can have a unit brought to your facility and run those trials and see. I don't know. Neither of those materials or adhesives are on the list of things that we generally have problems with. So I would think the answer would be yes, but again, I would rather test it to be sure.
And we have a question regarding, are there manual methods available for treating with flame or plasma, or is automation required? And are there any environmental or safety concerns for operators?
There are actually a few companies out there that produce handheld versions of some of these treaters. Generally, we do not do that. Robotic applications or conveyors are better because, again, you do need to control at least the speed with flame and the speed and the distance with plasma. So doing it by hand is a challenge. Environmentally, plasma does put off NOx. Mostly it's NO2, which is can cause dryness in the respiratory system. So you need a well ventilated, the word I'm trying to come up with, well ventilated room, or you need to ventilate the outside air if it's a room that's not So, but it is a very small percentage of the amount of air that you put into our systems. It's about 0.6% come out as an NO2, so it's a very low amount. So that's usually the only thing you have to concern about. But of course, both of the systems are hot. So you would want to keep your operators away from either the plasma, which operates at about 120 or 130 C, or the flame system is about 1100 C. So obviously you'd want to have barriers in place to keep workers away from those two things.
Thanks, Wilson. I have a question. Someone would like to know what type of liquids are used when making contact angle measurements?
Mostly it's water, and that gives you the polar groups, and in most cases the polar groups are what you're wanting to increase the surface energy. The other one that we use to get the dispersion energy is diethylmethane, and it is, again, it doesn't have any polar components to it, so that gives you both of those numbers. If you send up some materials to our lab and we use, in this case, the cruise measurement tool, MSA, to do that, then you're going to get both those numbers and you'll see the difference in what goes up, and generally is that polar component. It's broken down into the two, and sometimes with flame you can get some added dispersed components there, and what you're really trying to do in that case is match the adhesive with the different ratios you have with polar and dispersed units. But again, most of the time water is fine and will give you the polar component.
Okay, we have a question here. The person has an application that requires bonding to the ends of Etfe wires. However, the last 10 millimeters must be bonded, but the wire is exposed at the end. Which process would you suggest?
Etfe is on the list of things that is difficult to treat. Any fluoropolymer, so if it's got F in the acronym, it's a fluoropolymer, is going to be challenging. There's not a good open air way to do that. So our treatment methods would probably not be good enough. That might require a low pressure type chamber to do that treatment. And that would basically put a nano coating on the surface that would allow you to bond to it. But I mean, we can try it, but I'm not optimistic about treating Etfe.
Okay. Bonnie and Don, this would be possibly a question for you. Do you see hot melt adhesives bonding better with surface treatment first?
I would say it depends upon the substrate, but it would be, in my opinion, and Wilson knows a lot more about this than I do, that if you increase the surface energy of a substrate, almost any adhesive is going to have an improved bond strength. Do you agree with that, Wilson?
I would agree with that, but I think your first statement was perfect. It depends on the substrate. So some materials are already going to be high enough with surface energy that you're not going to increase that bond, because there's a level there where you're not going to go any higher. But yeah, I would think a vast majority of the time, surface treatment would improve the bond.
And the same person wanted to know if we have a surface treatment that is known to work well on liquid crystal polymers.
That's a good question. I'm trying to think if we've ever tried that, and I'm coming up blank. So that might be better offline. I can send you an email to whoever sent that, and we can discuss and try to figure out a way to test that. But I'm not remembering an application like that off the top of my head.
Those are sort of newer materials. So any work trying to create adhesion to those materials would need to have some effort put towards it to understand what they look like and how to work with them and what would work best with them.
We have a question on, let's see, where is it? Here it is. More questions came in and it scrolled on me. Can you recommend a treatment option for powder-coated metal surfaces?
We usually use flame on that just because most powder-coated surfaces are large and we're restricted by time, but any of the surfaces, well, the blown ion would also work. It just depends on the size that you would need to do, but powder-coated materials are treat very well. Again, it just depends on how much area we need to treat, how fast.
Bonnie and Don, there's a question here. A person has some applications that need a silicone with low viscosity or non-flow and good chemical resistance. Could you recommend some products?
I think the best path forward is to put in what chemical resistance is required and as many details about the application as possible, and pop that into the partner leads at ellsworth.com. We always start with experts who recommend existing commercialized products, and if they can't find anything, then they would forward it to the folks that do the custom formulation.
Excellent, thank you. Do polyethylene substrates have to have surface treatment for better adhesion?
I would say yes.
I would say yes.
I would say yes.
Right, we have a unanimous decision on that. Excellent. All right. Is an atmospheric plasma jet with air a good way of treating EPDM?
Yes, EPDM can be a little bit weird sometimes, but yeah, we do treat that on a regular basis. So sometimes we might use a blown arc. I don't remember if it was blown arc or blown ion that did better. I'd have to look at some tests, but yes, we do treat EDPM.
Question here. This person has a customer of theirs that has concerns about plasma cleaning and what it might do to the integrity of the chemical conversion coating on the metal core of the product being treated. Can you provide any feedback regards to whether plasma cleaning the chemical conversion coating will adversely affect the chemical composition and functionality of the coating? This is for an aerospace electronics application.
I've never heard of an application where we damaged the coating that was on the surface. Usually we're not hot enough and we're not over surface long enough to affect the coating. Now, I guess if you just sat the plasma in one spot and can let energy continue to heat that, then that's possible. But again, that's not generally how it operates. So I would say no.
Bonnie and Don, this is probably maybe a question you could just answer in general, but someone was wondering, this came in during your part of the presentation. Do you have recommended dyne level ranges for your various products? So I'm thinking, the question might be, do the manufacturers of the adhesives normally provide a target dyne level?
I'm not familiar with anybody that does that.
No.
Okay.
We do, if you look at descriptions of products, sometimes they do point you towards which substrates maybe they were designed to bond well to. And that's probably your best bet. But yeah, nothing about dyne levels.
Okay. Wilson, in flame treating, what surface temperature does the part typically get up to? Naturally, just want to make sure the part being treated doesn't get too hot.
Yeah, again, the flame itself is around 1100 C, but we're typically treating at speeds in excess of 75 feet per minute. So it kind of depends on the thermal properties of the material. So a metal is going to get a lot hotter a lot quicker, but we're still only talking a few degrees C in most cases. So if it's a plastic, it's going to be warm to the touch. If it's a metal, it's going to be hotter than that. But again, you're usually treating at a much faster pace, so that you're only increasing maybe 10 to 20 degrees above ambient.
Thank you, Wilson. We're closing in on our hour time here. We'll try to get to one or two more questions. If we don't get to your question, our experts will reach out to you after the webinar. This one has to do with surface treating wood composite panels, LSL, PB, OSB, when the surface seems to have been deactivated from high temperatures occurring from the process of producing the items. Can you surface treat them to help improve adhesion?
You can, but it sounds like, and I may just have misunderstood, it sounds like that maybe something was happening in the process that was taking some of the effectiveness of the adhesive away. If that's the case, then it might be a different adhesive that's needed. But I have had applications where plasma did improve those situations.
All right, thank you for that, Wilson, and that's a great example too of how companies like Ellsworth, Resin Lab, and Enercon can kind of work together to determine the best path forward to solve one of those application challenges. It's always best to kind of put it to the test. We will conclude the webinar today. I'd like to thank our panelists for their expert insights and our audience. If you have ideas for future webinar topics that you'd like to see us cover, please let us know. If you found the webinar informative, the presenters always like to hear any feedback you might have on the information they presented. So please go ahead and reply to us and let us know. And again, everyone will receive a copy of the presentation and the recording, along with a couple of other items and guides that we'll be sending out tomorrow via an email. And we'll make sure any of the questions we didn't get to today will get answered as well. I want to thank you again, and that will conclude today's webinar.